Thank you for joining us for this exciting live demonstration of Nexa 3D's revolutionary freeform injection molding process, or FIM for short. In this session, you'll see how 3D printing and traditional injection molding come together. This integration offers amazing freedom and boosts productivity, which drastically reduces tooling time and costs. Today, I'm thrilled to be joined by Carsten Jarfelt, our resident FIM expert at Nexa 3D, and Kubi, president of APSX. And with that, Carsten, go ahead and take it away.
All right, thanks all. I'll just drag up some slides. Thanks for the intro and thanks for joining today's session. All right, I hope you can see the slides. Slides are interesting, but products or parts in hands are much more interesting. So let's do both during this webinar. Freeform injection molding, that's a lot of stuff to cover, so let's get started. But as Tyler said, use those Q&A buttons, or that Q&A button, to put in your questions, and we'll get back to them either end of this presentation or afterwards, if it should happen to be an overload of questions, as there normally are. Myself, pretty boring slide, but I spent 5-6 years doing freeform injection molding. I kind of started a lot of the US activities in talking with clients, markets, investors and stuff back in the days about what is freeform injection molding, what can you do and what can you not do. And I think it's mainly those 500-600, imagine that 600 clients facing projects that have given me and us at Nexa the insights to look at this both with curiosity and a grain of could it be done, would it mold, can it actually happen and stuff. But we have platforms out there, Nexa 3D, our printers, our resin, our software and stuff like that sits with a lot of clients. But mainly those client-facing projects have brought us a lot of insights, because people want to talk about what they haven't been able to do, and we do listen every time. Over to our partners now, Kubi at APSX, who has been going on a journey with us for the last almost a year now, with combining their cool technologies with our cool technologies, so we can offer you anyone kind of a package that fits your actual needs. So Kubi, over to you.
Thank you, Carsten. Welcome, everybody, to our webinar today. I'm Kubi here at APSX. We have been selling these APSX PIM desktop injection molding machines since 2017. It's been about 6 years. Our specialty as a company is to downsize industrial machinery to portable, efficient, and affordable options for everybody. Our goal is to make them accessible to everybody, not just the ones who has budget for space. And our company goals have multifaceted ways. So first, one of our goals, our machines have to be affordable. And by saying affordable, that's not just the pricing and also the size, because for some countries, for some cities, space is also a premium asset. And also, our machines are sustainable. That means you can minimize your waste, and you can be environmentally responsible as a company or as a person. And another goal of ours is our machines have to be efficient. That means you shouldn't spend a lot of time to set them up. They are easy to learn, easy to set up. And our final goal is our machines have to be agile, because if you go to market faster than your competition, that makes a huge difference. So our machines can provide a faster to market approach. Other than that, maybe we can talk about our typical customers. We have customers from colleges, research institutions. They can be individual, like an inventor type person, or a global company. It could be a research and development division in a global company as well. Also, our machines are in Navy, Army, NASA, that kind of institutions as well. And as I said, it's been in the market since 2017. So if you need more information, you can visit our website or send us an email directly at any time. And thank you again.
All right, unmute is a good thing. Thanks, Kubi. So in general, we're going to refer to FIM, FIM, or whatever during the presentation here and during the discussions. And that does mean freeform injection molding. So don't get confused. I just wanted to make that very, very clear that it's the abbreviation that no one else knows than a few here. But what people are starting to noticing is that it is exactly as Kubi said, it's enabling teams to do certain things. And today we're going to look at parts that look like these that would be very hard to tool up for in any other way than this. And we're also going to look at what it actually means to have a technology backing your decision making, because a decision to do something or to not do something are both good decisions if they're based on data. That is sustainable and maybe impactful if they're done on gut feelings. So what freeform injection molding is doing on the back end of a lot of technology and software is actually enabling you to make decisions, validation studies, and give you options to perform or stop doing exactly what you shouldn't do at the current stage in the current design and whatever. So it's an enabling technology stack that gets you to places. And I think the place we want to end up at after this webinar is actually on your end of this conversation. What does this mean to you? How would that impact your business? How could you gain competitiveness? What could you do that is different than what you can do today based on your current options available? And then it's a lot about, why using FIM? What is it? Who is using it? How does it look? That's the most important thing. That's the most interesting thing. In our world, hands-on as we can be on these cameras here. And to you who sees the screen here shared with slides, I do also have a couple of cameras. Let me introduce them. This is the most boring one. That's me. This is the top-down one where I have all kinds of products that we can talk to if you have questions. Then we have a close-up over here because we also do metals, MIM, SIM, ceramics, and soft stuff. And you would have no clue what I'm talking about unless you could see it. So we have a macro camera. And then behind me, just as Kubi was showing, I have Kubi's amazing machine and our modular mod bases. So, during the Q&A, feel free to refer to any of these things that you just saw besides, I wouldn't say boring slides, but besides just seeing slides. All right, so back to your end of the stick here. What are you getting from potentially implementing what we're talking about? Well, if you can work with designing in new parts, new materials early on, that's maybe a business for you. If you are able to customize, adapt, and do alterations on the go of very, performance ready and already validated parts, but now in need of a certain update or slightly modification, this is a way that you can use FIM, freeform injection molding. We have clients totally focusing on using spare parts management, using our tools for spare part management because they have so low volume and so high performance criteria that they can now use this as a technology. But if you think about this product life cycle, how many places you are met with certain choices and non-choices or non-options. That's why freeform injection molding gives you that smooth transition between actually not what we can deliver as a technology for you, but what are you actually going to make with that technology? And we are moving up and down that product life cycle curve all the way during the presentation and discussion here. And I think back to the why. Why is, in my opinion, often about the business, about the value behind the technology and an offering, whatever it could be, in this case, FIM. We touched upon it already, but you can do more and assume less because you can actually make parts. You can test 7 gate position locations on your part on the same build plane maybe, or the same day or next day. And then you will know which one of those 7 ones are interesting on the 6 ones who you shouldn't pursue further. So that's doing more and assuming less. And then just the fact that you go from idea to parts in a very short time without compromising, without being a an amazing tool or mold make designer is also value. And then you call, I know it's a pun right there, but you call the shots, right? With the platforms that Kubi is standing in front of, you can see it's a 10 feet tool line with everything you need, from printer to cleaner, curer, demolder, and an awesome 5-ton mold unit, right? So you call the shots because you call also the supply chain limitations. You are the one, and then you can also sacrifice the time. You don't have to sacrifice time on heavy resource loaded tasks because we have software helping you. We have the whole doing it versus simulating it availability for you. And then just the fact that you can get to a next step on your development cycle, which is all about moving forward, have progress. And I think our good partners over at Wilson Sporting Goods is putting it like this. And the right side of the slide here shows very traditional, the risk curve for traditional injection mold tooling. And the green area is the risk curve for freeform injection molding tooling, because you can literally fail quickly, which is good because then you can fix what you didn't want to do and try again. And the cost of getting to that, hey, I failed, let's do it over again, is extremely low compared to any other tooling, regular ones or other printed toolings options out there when you are in the molding phase. These words comes from a guy, the director of advanced manufacturing, Glenn Mason, who has 33 years of molding experience and 3 years of freeform injection molding experience. And when he puts it to the internal discussions when they onboarded our platforms years back, they said about leaving resource-heavy tasks behind is not having to design for manufacture a part, not having to be a mold designer or do a mold design, and not having to build a tool but print a tool. The part DFM and mold design simply was taken out of the lead time, and the print versus build was shrinking the time to actually make a tool dramatically. So I think 3 years back they said they went from 12 weeks to 7 weeks of lead time. I think they're lower now even, but they cut roughly 50% of lead time on everything. And that's why you get to do stuff like this. Just 4 examples taken straight out of the goodie bag. Upper left corner, living hinges, caps, PP, 100 recycled PP. Upper right corner, PepsiCo's blue bottle or blue cap in their HDPE for their bottles, a project they nailed pretty quickly, as you can see, using our technology. Medical device adapters, anything in medical device requires certain materials. Well, we can work with those. Our technology is also biocompatible, so we don't change the properties of the material you want to use. And then lower right corner, badass 40% glass-filled nylon for automotive as an example. But all coming to life in a pretty fancy, rapid way, but also without compromising what you're setting out to do. Original launch materials, step files that you want to produce, and with our software, you can get some help in doing the mold files that you can print. And printing is where it all starts, and where most, I would say, prototyping projects start out in printing, because you want to explore stuff like design freedom, fast delivery of your first thing in hand. And then at some point you want to move on to molding. What we kind of said is those 2 entities, they bring the best. They bring the best from the freedom, and they bring the best from the materials and processes. And you always had in the past to change between 2 technology tracks, but now you don't, because you can actually get the best of both worlds, so to say. You can start up with the additive space, which brings you all that short lead time and design freedom. And then you can actually go over and take the versatility, scalability, and all that quality materials that are known to reside in the molding, injection molding part of the domain out there. Combining those, you will actually get where you can go from an idea to a tool to a part to a validation thing seamlessly. You started out in molding, you just happened to use a printer to print your tools. But that same printer, the installed base, can also print you the parts. So it's the beautiful handshake between, are we looking for form and fit today, let's print a part, or we're looking for form fit function, let's mold the same part. But let's start using the same installed base equipment to print in different resins. One can go to tooling, one can go to part level only, you could say. So we wanna bring you that, and we wanna make sure that you don't get held back by technology limitations. We give you a hammer and a pretty good tool shed, but we know our hammer and tool shed sits very well with other tools, and you should use a combination of tools. FIM is just a pretty wide applicable starting point for designs, materials, and speed to something. So how does it look? The FIM process is in verbal state. You could say you have a part design that you can, through our software, convert into a tool design. Since our tools, as you'll learn quickly, can dissolve, are soluble, sacrificial, if that's the today's task, then you don't have to design a tool with complicated collapsible cores, slip angles, undercuts is not an issue, and so on and so on. Okay, you design your part already, you turn that into a mold design. That mold design you print on one of our resin printers in a tooling resin called XMold. You will hear more about that quickly after this slide. Then you go to the molding domain. You might have Kubi's amazing machine, the 5-ton that I have behind me as well in my home office. And I think our printed tools handshake with many mold units out there. It's not about what brand it is, it's what gets you going and gets you to places where you can decide stuff. Okay, you have a part, you have a tool design now, you have a printed tool that you take to a mold unit and you squirt material into it, whatever you want to do. And then you have now a part sitting in the tool that you want to get out. If it's a complicated part with lots of stuff going on, you can dissolve your part out. If it's a pretty basic A and B kind of part with which allows for that, you can open it up, depending on material, design, a few other things. But that's literally the process. And if we were to make a video shortly showing that, it would be something like this. Let me just click it. As you can see, the XMold is a blue resin. You print it on any of our resin printers. You take it to the clean and cure station, and after that you go to the mold unit and you put it in. This part here in the video is actually a 50-ton mold unit where we use a spacer that we print also in XMold. You'll see more about spacers shortly. But we use that to, preserve most XMold, print the least, demold the least. But as you can see, the part coming out still in the tool here is a pretty complicated design gimmick, I would almost say. And the reason why we made it that complicated is, of course, then we make that statement that it could be almost anything you can think of. And then we're getting to that solubility stage. And yes, this is a time lapse, so it does not take 8 seconds to dissolve our tools. It takes maybe overnight for the smaller parts, the impellers that Kubi are showing later, or next day or 2 days for larger volumes. But there are many ways you can accelerate that project or process. But as you can see, the tool itself is soluble when needed, if needed. So just a quick recap, because we're covering a lot of ground. Printer, a resin printer of Nexa, a clean and cure unit, XMold resin, and a demolder to get it out chemically using sodium hydroxide, an alkaline. Those printers, that line is what we call the FIM line, the Freeform injection molding line. That comes in desktop size, everything, and industrial size, everything. So bigger printers, bigger cleaners, bigger demolders, or as we show here on this slide here, the desktop everything. And I think let's spend just a few words on the resin before I give the ball to Kubi. XMold is that blue stuff you've been seeing now in different variants, like tools or sitting with parts in them on the video as well. It's an amazing resin that brings you access to a lot of stuff like high temp materials. Our tooling resin allows you to inject, parts that are, 400 Celsius scale of temperatures into them. So peak, ultim, PEC, peak, PAEK, other high temp materials you can use with our tooling resin as well. It's also that fact that gives you the access to all the mold units out there with the standard molding pressures that you're using, and the fact that it's soluble. It's giving a lot of extra value, as you'll see. And a second nifty feature is that it's also non-stick. You will see parts later that are just releasing from the tool or parts of the tool in XMold because of that feature. And then for medical device and food industries, it's interesting that it's a biocompatible process in general that allows you to work with materials that are otherwise hands off because of those strong regulatory domains. All right, a lot of ground covered in a short time span. I'll give the microphone and the floor to Kubi because I want Kubi to share some of that insight. What happens when you then plug in a desktop injection molder, like you just briefly introduced to this whole desktop line of FIM? Magic seems to happen. So Kubi, I will give the floor to you, and I will actually stop sharing slides for allowing for full screen view of your window.
Okay, thank you, Carsten. So can you see me? Okay. We can start with these two units we have here. So this is the 3D printer. This is the wash and cure unit. You can use those to print your blue stuff, XMold. So they're injection molds or tools, we call it. So in this case, we have a tool for a propeller design, pretty complicated part. Then next to it, you can have the molding unit on the floor. And the final step is to use our injection molding machine, APSX PIM. So the machine is already warmed up to 192 Celsius to use a polypropylene yellow color PP. So it's good to go. We have the pellets here on the hopper. Whenever we are ready, we can just insert this tool into the cavity, the mud base. Then it's going to be about 90 seconds cycle time. I'm not sure if you can see me here, so let's get a little closer. Okay, so I'm gonna hit, I'm gonna insert this first, and hit run. So it starts like that with the clamping, and the injection pressure is built on the left side. So it's completely clamping process, and down it's going to be injection, inject it properly, closed. Now it's cooling, and after that it's going to go back to home position. So basically the mold is going to be open. The difference between the 3D printed molds and the aluminum molds or metal molds, the cooling time in this case a little bit longer than metal molds, so because it takes time to cool them down properly. So in our settings, it's 45 seconds cooling time. That's why it's holding it at cooling stage. And other examples would be these that you can make by using our machines. And it's going to be open. Now I'm going to pull it from the base, I'm not sure if you can see clearly or not. That's the finished injected part. If I try to open it, let's see if I, so you can see it's done, but we need to dissolve the tool afterwards. So it may take an overnight process to get the finished propeller. I have these. I can show you. So at the end, it's going to look like this. And other versions of the similar propeller would be like that. So that's it. So that the whole process in this case took 87 seconds, and it was a successful shot. If not, you need to play with the settings until you optimize everything, and you can save as a profile and go from there. So back to you, Carsten.
Thanks, Kubi. And I just have, my mind is blown every time I see this, because first now you see what space it's taking up, this line of tech. But when you saw the ease of getting complicated parts in hand like Kubi just did, I think it's worth noticing that, as you might see behind me, I have a similar mold unit in my home office here in Portland, Oregon. And I think when I queue that up for a client conversation, people curiously peeking in through the screen here or the cameras, wanting to learn more about that. The fact that you can print the tool, put them together, put them in a mold unit, click run or go, wait the amount of time specific for the part and material, and then next step is to either open up. I don't know if you noticed, but Kubi was able to just wriggle it open, and those 4 sprues, or those small 4 strings of yellow polypropylene I think we're using here, are just vents to indicate that the material has filled the cavity, the void in the tool, and so on. But the fact that one side just gives because of the non-stick, and the other side with the complicated propeller design gimmicks, they will have to be dissolved because of otherwise very complicated metal tooling. And I think that's the beauty of that.
And you can use this site again and again. So just one site has to be dissolved.
I think that's why we call this enablement, without us having a specific agenda for you, but actually to get you going and get you to try what we're talking about. I'm going to bring up a slide here again, because nothing beats seeing the stuff, and we can show up close. But I think what you saw happening inside the mud base, you could say, on the unit, if you imagine that you have a mold unit like the one behind me. Let me actually walk over to my mold unit. I hope you can see. Actually, I'm gonna unshare this one, and I hope you can see my full screen behind me here. So I'm gonna walk over to my mold unit, and what Kubi exactly showed was that all the complications of the part design is captured in the stuff we've printed. So all the part features, all the undercuts, all the things you want to actually, it's all about the part. So you can get to a part easily and in a validated way, repeatable way. That's the game here. So it's not so much about what happens on the mold unit, besides that needs to be consistent, predictable, and uniformly happening every time. And that's why we use this mindset that we call the mud base. And everyone familiar with molding will know what a mud base means. But this is maybe one level up or different from what you normally see. So what we have is a block of aluminum that is cut to fit the mold unit here, the APSX PIM Desktop. molder. In order for us not to waste too much XMold, we kind of size things down. In the impeller design case, it could be a mud base like this. This is just a printed spacer in X ceramic, a material that we also allow you to print in on the same printers as XMold, so the Nexa resin printers. And in that one, we could put maybe a tool, of course not filled, but an empty one that has this complicated part that Kubi showed, and out comes the job of the day, which is the impeller. But imagine you had a slightly more, I wouldn't say complicated because the impeller is complicated enough. This is also an X-ceramic spacer. But if you were to do today's design where the part might be something with a lot of physical important activities like these, a living hinge that has both the closure function and the actual living hinge going forward. If you can print a tool that you can actually almost go near net shape on, so what you're getting is a little bit of blue XMold tool around. When you can then take that approach of mud base adapters to the next level, then you would put the two-part tools, which we have printed on our desktop resin printers, into the mud base here, which is, imagine that this is sitting in the mold unit because it's all happening kind of in here, so it's difficult to see. And then you will inject that one, pop it out, as Kubi said, and put that to sodium hydroxide because of those pretty complicated design features. But that's, again, a process that is possible because you can do like that. And I think when you can work with the mindset of what you're setting out to do, and you can get your technology to follow you to places where you want to go or potentially want to go, that's where we see people, I wouldn't say have fun or smile, but definitely, get to places they couldn't do. And I think, let me see if I can just go to full screen again here. So this is what I was trying to show. Adaptable mud bases, small things, big things, and the APSX unit can shoot up to 1.8 ounces of material, which is a lot of material for such a desktop-sized unit. And when you use those mud bases and that approach, you can shoot, small or big parts, but you can get there pretty quickly and on your own terms in your own time. And I think this is just a way of saying what I just showed over there, that you can literally put anything in these spaces. You can also optimize for throughput by putting the least XMold and the least dissolvable tools into action. And with the APSX unit, that goes up to, what is it, Kubi? Is it 300 and how much?
It's 315 Celsius.
So 315 Celsius will get you to a lot of materials already there. And if not, I've heard something about higher temp units becoming available, but I will let Kubi cover that in the future somehow. But the playground is extensive with that mold unit, with that setup, and with that temperature range. If you notice that Kubi put the hold time and the cooling time to much longer than you would normally do in a metal tool, that's because the XMold, the blue printing resin, is a damn good insulator. And that means the part is actually sitting in a tool where it can sit in a pocket of blue resin, and you can transport it to the next step in the process. But the holding time or the cooling time is a little bit longer simply because of that. But if you look at what happened in getting to that, when we talk about enabling you to go places with this technology, it's also about you being able to do things pretty rapidly. So the tools that we are demoing here today, they can fit on the desktop build plane, which is the XiP Desktop unit of ours. It can fit 4 complete sets, so 8 halves of those tools that we're using for demoing. And they will print in 28 minutes. So around 7 minutes per tool. And keep in mind, they don't need to be 4 of the same design tools. They could also be 4 different sizes of tools of the parts. It can be meant for different materials that you're going to inject into them with different shrink rates. So you have adjusted the tool sizing for the shrink rate that you get from the data sheet of the molding feedstock and so on and so on. That part is regular molding, but getting to tools you can not only produce, but also have maybe designed yourself using our mold generator software that comes with our platforms. That's another enablement. So if you were looking at what Kubi just showed you live, would look like in a project overview, you could say. So 8 halves, 4 tool sets in 28 minutes. And as you also saw, half of that tool could be reused because of the non-stick. There's almost no impact to that tool. Of course, if you go several hundred parts in that tool, some degradation might be noticed. But until you see that, until that matters for you or is impacting for your results, keep using maybe what you can reuse. So 8 halves, 4 tools in 28 minutes. You clean and cure them in that UV cleaning curing station, and you clean them in IPA. We have processes all described for that. Then you injection mold them in the APSX unit as shown here in a couple of minutes, all the tools. I saw Kubi did yesterday on Memorial Day, 60 parts in an hour, or 60 parts in 2 hours, I think it was, for some demo we're doing for a trade show later next month. You can split tool right there to check if they're full. You can demold the rest overnight. So literally you're talking about a 24-hour cycle or maybe 1.5 day cycle, including a night, whatever, to get to parts in hand. And that could be, your design and almost any design. And when you look up closely, which is hard on these web cameras, but when you look up closely, this is the part that we kind of designed as a variant of that gimmick, and they're printed in 100 micron C layer access on our desktop printer. Those tools, but that goes for our desktop printers and our industrial size resin printers as well. You can set those settings to fit today's need. Then we have had a lot of joy in working with a lot of different clients and industries out there. And I think it's always a good question to reflect on, where does this work for me, and what would be a good way of having some references from others who are using this, right? And I think what we see is an industry where materials matter. It comes from either performance, regulatory, limited choice by straight out of the gate can only use certain things. We've done projects for clients who could only use Optima LT3 implantable PEEK. Then it's a joy to say, let's try that. And PEEK is one of our high runner materials, so we know it works. But it's always nice to enable a client out there to actually continue using exactly what they are launching the parts in. And I think that's where we come in and say, we are not masters of everything, but we are extremely curious. So we have infrastructure in place that can grab your attention. As you need a service bureau that offers this, we have that for you. Do you need the platforms yourselves? We can allow you to get some platforms for sure from us, from Kubi, from all our resellers. But one thing we have a difficulty and hard time accepting is if we can't have that curious conversation around what would this mean to you, right? And in those industries where we are present right now, it means the whole thing to these teams out there, that they can decide to progress those projects or stop them right there, take them back a step, refine what they saw, the errors they made today, fix them and move them forward tomorrow. And I think, performance materials is one thing, and then also low volume. You saw the speed of things here. We're not talking about an industrial process where it's going to spit out thousands of parts every minute. But we're talking about a process where you will get to know which part to back with all your resources and budgets to get to many thousands, because you're going to end up most likely in a high throughput situation where you go to metal tooling, but what metal tool to cut for what part, for what functionality and success criteria. That's our business of helping you to get there. And then there are lots, as we actually started out, there are a lot of industries where low volume is low volume, high mix is their business. And low volume should not be associated with quick and dirty, scrappy prototyping, because there's not a lot of prototyping when you do low volume FIM, low volume freeform injection molding, because you're starting out with the material that you want to launch your part in. You're using the step file design of your part to create your tool. And from there, you're molding your first part in a very short time span. So we don't call that prototyping, we just call that low volume manufacturing. And I think the same goes for some of our clients, and maybe you've seen this with PepsiCo, but we're extremely proud of how they adopted this technology, especially when you think about what you could refer as to a critical path project. What is a critical path? In our world, it is all the elements you need to combine together to get a product that you can decide certain things based on. So if all the parts in the given product is not there, someone is the bottleneck, someone is waiting for something in order to decide those important final steps. And in this case, Team PepsiCo was already blow molding bottles with our technologies using XiP printed shells that they used for the liners of a complicated blow molding tool. But before you have a final product, aka a bottle with a cap, you had something on the critical path. And that's where we stepped in from a curious point of view and said, what are we looking at? And then we turned around together with the team quickly in a matter of days, a handful of different designs so they could move forward without having to jinx anything like materials. They just sent us their materials to use and their design files, different designs they had in mind. That's a lot of reduction, as you can read on the slide. Time reduction, 93%, total cost reduction, 96%. But it's also a lot of enablement on many other things that you can start to explore. Same goes with our team over at Wilson Sporting Goods. Total other end of the scale, bigger part, much bigger part, by the way. Tough material. We don't even know what the proprietary carbon fiber material is, but we know that it matters a lot when you can print tools overnight. That enables you to have 25, 30 bats in hand next day, where you used actually a 418-ton press to put A and B tools together, and like an insert to a bigger metal tool. And from that, you can get, if you look at the slide right now, you can see in the furthest right photo, there's a close in on or zoom in on the bat surface. There's some in-mold texturing that goes into that carbon fiber performance material and so on and so on. And there's some design changes to how the bat rebounds and stuff. But all of that is in the hands of the client wanting to explore stuff. And our contribution was merely just enabling them to explore without having to wait for someone else, or without having to almost use the right material, or almost have to shortcut or dumb down the part design. Here they took the part design they wanted and molded it same day, actually, or next day, from having an idea about it. And that's, again, a lot of value add on the client side. Another client, I don't know, Team Blue and Team Red here, but we are not allowed to show any parts from the Coca-Cola team, but the verbal quote here from Kyle Layfield is dear to our hearts, because he and the team are touching upon some true values of ours, and that is having that complete design freedom, as they talk about, functional realism, as you saw the living hinge cap before. Functional parts testing is just one step up. Extensive material options, meaning we don't have a short list as such. And then those final physical characteristics that enables advanced R&D to work without the traditional constraints. That warms our heart. All right, enough tear shedding on all those great cases and a lot of words flying on the screen here and in demos, and so you can get started as well. And of course, we're in the business of enabling you, and we have small, big solutions, both Nexa 3D and APSX are producing all our parts and shipping them out of the US. So you will get US made, US shipped parts and systems should you want to go there. We can help you get projects started, and we can get you to explore what it would mean to your business of having the opportunity to work with freeform injection molding as an enabler. And I know it's going to be the only sales slide here, but that complete package that you saw, that we kind of have demoed from different angles during this webinar, is less than 30,000. That includes everything you need to get going: software, printer, cleaner, curer, demolder, APSX's amazing desktop unit, mod-based system. I don't know what I forgot, but you will have what you need in that package to get you going. And I think the fact that it just sits on the trade show floors, in demo rooms, in labs, in units, in OEMs' garages and startups' garages, and makes it a very agile technology platform to use, and affordable for the fact that it's a damn good printer, it's a damn good tool maker, it's a damn good tool designer. You can mold your parts, you can demold your parts, and you can make decisions based on, as we were starting out to say, by doing and not assuming. And that makes us proud that we could potentially enable you to do as well. I'll hold for now because I think there could be some questions. I didn't check the Q&A, but let's open up and see what's there.
Yeah, lots of really great questions, and then that's super exciting stuff. Great presentation, guys. I'm going to start with a very specific question. I'm going to field these to you, Carsten, and you can decide to send them over to Kubi. Very specific question. We often create components with small features that are 0.25 to 0.5 millimeters. Often molding companies have said that they cannot mold these due to pressure required. With a 5-ton capacity, would the injection molding machine be capable of creating this size of features? Also, what is the minimum maximum shot size of the machine?
The last part was what is the
minimum and maximum shot size of the machine?
Okay, I will take the first. Kubi can take the other. But again, all projects using FIM is based on details, based on materials, based on design files. But flying in from 30,000 feet here, we can only get as precise as the tools we can print on our printers, and they are 50 micron in all axes natively, roughly. That being said, you can use things we haven't even covered in this presentation: hybrid tooling. You can insert embed metal pins, cores into these printed tools, or you can drop our printed enablers into other metal tools already there. So there's a hybrid approach we didn't cover that can get you places where only metal can go in that mix. But judging from the question there, let's go and explore that project. You know where to find us. And I think the fact that you can work with low pressure molding, we don't need the 5 tons to go places even. But since this blue stuff here that I love to show off is a very good insulator, you can make parts that are very complicated, but also material flow paths that are pretty complicated normally to do, to make actually happen because of that insulation effect that brings that material further into the tool. So, but I mean, Kubi, maybe you can touch on the minimum max shot size of the APSX.
There is no minimum size, but the maximum size is 1.83 cubic inches. That's the maximum shot size capacity. But there's no minimum shot size. So whatever your cavity volume is, it's going to be filled in.
Great. Next question. How many times can an outer printed mold insert, as shown, be used with successive inner freeform molds during or before degrading? So how many successive inner freeform molds before degrading?
All right, cool question, and thanks for putting it out. Now we have my top-down camera here. So this tool here, this tool set, made this medical grade adapter in medical grade TPE. So flexible but hard, a 70 short. This tool set made several hundreds of this part here. Because of the flexibility of the part, you can wring it off the center core. Because of the non-abrasive material data on this one, you could have several hundred. What you would need to do, because of the insulation, is to print a couple of these sets and then cycle them so they don't get too warm. But then you can cycle through a couple of these tool sets that will maybe set you back $40 in resin and print time. But then you can have several hundreds out of these tools. So that's one way. The other one that Kubi showed, let's show it with the PepsiCo cap here. If you see the cap sitting here, I know it's black, but it's still the same. We reuse this part here quite many times, 50 to 100 times, because it has a straight pull. The temperature of material does not degrade the tooling, so several hundred times. But again, sometimes you just get one, like this one here. If you want this out, this complicated lattice, you'll have to dissolve your way out. But hey, if you want an ABS injection molded lattice, maybe it's worth it. So there are quite those flexible options, I would say.
Great. Are there any alternatives to sodium hydroxide for demolding?
You can't tell that there's water in this bottle, but you can use water. And it takes longer, definitely longer. But if you would happen to have one of those of ours, let's say, non-compatible feedstocks out of the gate to inject into parts, polycarbonate and alkaline does not have a good match. That does not mean that you couldn't do an X-mold facing surface against the polycarbonate part that you could pull out. But the moment you have a polycarbonate part that you want to put in the dissolving phase using sodium hydroxide, that could be a place where you could turn to water and it will come out. And in the demolding phase, we both raise the temperature and we have active stirring with impellers in the demolding unit. So you can have some help in accelerating that.
Great. Can you describe the storage and preparation of various plastics, such as humidity mitigation, drying, preheating, and any additional equipment needed to enable this?
Maybe that's for you, Kubi.
Is it related to like plastic pallets, like resin?
Yeah, humidity mitigation, drying, preheating.
Okay. Mm-hmm. Yeah, there are different types of plastics. Like for example, for our showroom, we only use polypropylene and HDPE. So the reason for that is they don't require drying process. Other materials such as ABS, nylon, Delrin, you need to dry them before you use them on the machine. Drying is basically baking in an oven settings, so just to get the humidity out of the resin. Otherwise, you may see like bubbles in your parts or like excessive gas exhaust during the injection molding process.
And then a follow-up, the APSX unit needs to be loaded and unloaded from underneath. So does your table need to have a hole or space in it to load the part?
It doesn't have to be from the bottom. You can use this gate and load it from the front. So for our convenience, we chose to do it that way. And open desktop helps in other ways too. You can reach from the bottom. Also, if you have like a mold with ejected pins, the part would be ejected automatically and they can drop into your bucket and fill that bucket for yourself. So that's the reason we have a desktop like that.
Great. And a question for you, Carsten. If the mold is going to be separable, can other resin be used for the mold, such as X ceramic, or is that X mold the only resin that has the temperature resistance and lack of chemical compatibility necessary to use the molding?
It's a really good question because a lot of that lies in testing real life, what works, what does not work. And we haven't done the full circle on the X ceramic and other things. But if you are looking to get to a resin that you can print a tool out of that has the least prep, the least pre-work in what would happen, then I would choose X mode over any of our others and actually any other resin because of that give, flex, non-stick approach of it. If you are then to optimize what you just learned from the first shot, you might be able to do like I showed over at the mud base. You can actually use XRAM as a spacer. We're also using XRAM as a as a mold tool, you could say. But the handshake between what works first out of tool, what needs to be optimized to maybe for throughput and so on, lies in exploring. But those are options. But the first one I would choose, and I'm biased, sorry, is XMold, because you don't have to worry a lot about will it stick. It will most likely not stick, which is a good starting point.
And follow up to that. So ceramic-like materials, XMold, and then directly to aluminum base. What is the intent for those differences? Like, what's the advantages of those?
The advantage is flexibility and you being able to save XMold. I'm gonna show this one over here again. If you can print this amount of, get you this part, or you can print this amount of XMold, it's a no-brainer. You want to print the least. But what you notice here is also by printing a spacer to gently kind of sweep around the whole design here brings you a very uniform support from, because XMold is slightly soft, you could say, but it's hard enough not to give, but it's soft enough not to break and be rigid. Back to the question before, what makes sense to use. But then a very uniformly pocket shell mold kind of tool is only possible if you have this. Most do not have a CNC unless they contact APSX and get a desktop CNC, which they also provide. Others, if they have the printer, they can pour in the XRAM and print spacers in XRAM. So that's why we use the XRAM, because it comes from the same, you could say, print opportunity, the same tech stack that your printer allows you, and that's why. But you could cut it in aluminum if you had that option as well.
Awesome. I think we have time for a couple more questions. This is a good one. Can you explain how to create the file for the mold itself? Is there any special software tools or needed to do that?
I mean, for many years, freeform injection molding was just a way of saying, and I'm going to show this with a part. You have a part design, box it in, remove the part design, put a gate, couple of vents, print it, shoot it. That's the basic assumption of how you design tools. After that, we noticed that most are not that capable, and not everyone is that free spirited. So we have something we call the mold generator software that will take you from it's not a magic tool where you drop something and boom, suddenly you have everything right there. But it's more an augmented process that tells you, is this a cosmetic site? Should you put the gate there? What is the intent here? Should we split the tool or should we just leave it as a mono block tool and so on and so on? But that's the mold generator software. And that's something we deliver together with the systems. And it's a good starting point.
Great. We'll end here. The question is XMold material compatible with mold design with ejector pens?
I mean, it is, yeah. We use, I mean, Kubi, maybe you can touch upon that because we use that.
I don't have a mold with ejector pins, so it's XMold, but it's compatible. So it doesn't matter if it's XMold or different material. So you just need to insert a ejector plate at the back with ejector pins, and it has to be custom made for your part. So there's no like generic uh, ejector system. It has to be designed for your part. So it has to be specific locations, specific lengths, but it's compatible. Yeah.
Mm-hmm.
Awesome. Well, we'll go ahead and end there. Thank you, everybody, for your questions. A live recording of this demo will be sent out shortly after we're done here. Thank you, Carsten. Thank you, Kubi, for speaking on this exciting technology. And thank you, everyone, for joining us and part of your day. Have a great rest of your day.
Thanks for joining.
Thanks so much. Have a good day.
Have a good one.
Thank you.
Bye.